I'm going to make you all quantum experts in 15 minutes. Are you ready? Okay, good. It's late in the day, so I'm going to make this a little fun. It's quantum physics. What's not fun about quantum physics? So first of all, I wanted to explain that, actually, let me go back first. I'm really here not to make you quantum experts. I'm not even one myself, but I'm hoping to get you excited about all the things going on in quantum science and technology. You've all heard the hype, right? We all hear all these big things. But it actually is really interesting, but there's still a lot to do. So let's talk about it. Are we going to buy the $100 million quantum computer? Is it time? I'll get to that. But first of all, I'd like to know, who's aware of qubits? Who knows what a qubit is? All right, we've got some hands in the audience. That's great. We're going to talk a little bit about qubits because that's really important. No worries, I'm going to explain it to you. So we'll get to qubits and then we'll worry about the $100 million computer. I work at Oak Ridge National Lab. It's one of 17 Department of Energy laboratories. That's a lot if you think about it. It's the largest funder of science in the world if you think about it. And we are one of the Office of Science-supported laboratories. Along with our friends at Argonne and Berkeley, we investigate these basic science discoveries in many areas that you guys are familiar with. Materials science, chemistry, fusion, nuclear energy, vehicle technologies, manufacturing. I could go on, and I'm sure I'm forgetting some of my friends in the audience, but we do a lot of that. And that's really important because we work then with our industry partners and private and public entities to translate that science into things that we care about. And that will help that will help citizens everywhere because that will allow them to take advantage of the technologies that are developed. For example, biomedical research, detecting depression at an earlier age, more efficient washing machines, and my personal favorite, which is more accurate and long-term weather forecasts, especially living in East Tennessee. You have just 2.5 hours going east here across the plateau, nestled in the Smoky Mountains, almost 7,000 employees who work on these problems every day. And so it's a real opportunity to bring all these people together and work with the rest of this area to do some really great things. One of my favorite toys, I sit in computing, is Frontier. And I'm not allowed to give a talk about Oak Ridge without saying the largest computer in the world, the fastest computer in the world for science. And so that allows us to do science that's never been done before. No one's built a computer this big before. And we have a history of delivering these machines over the past decade. And each of those has never been done before. It's hard. We work with our industry vendors who get the contract to build it, and they've never done it before either. So you have to think about, we're hooking up all these different things together. We're hooking up the processors, the network, the software, and then the applications who have never run on a computer that big. All that has to happen for this to be successful. And so it takes a lot of hands on deck, not just at Oak Ridge, but with our friends and collaborators at other places. Think about it this way. Your iPhone in your pocket. When I showed up at Oak Ridge in 2007, just where Frontier is now, you had the Phoenix supercomputer, which ran at about 200-300 teraflops. That's the same amount of computing power as your iPhone is right now. So the point is, in 15 or 20 years, you're going to have a Frontier in your pocket. You're going to be able to do all the things that we're doing now. It won't be 30 megawatts to run, I hope. So we have to do a lot of technology development to get there. But we do it first at the labs so that you can then develop the technologies and build the thing for the future. In about a month, a bunch of tech nerds are going to meet in Europe and decide what the next biggest computer is. They do their top 500, and Frontier's unlikely to stay #1. And that's okay. That's where we're going. And working with our friends who are doing these bigger computers, they're going to deliver it, and we're already on to the next computer. We're already talking about the next computer in line and then the computer after that. And that's when it gets interesting, because now, just like Titan, which was our first system to get GPUs, what the heck's a GPU? My son knew, he was gaming on one, but it turns out they're great for supercomputing. And so we're now working on quantum. So are we going to buy a big quantum computer? Are we going to do a hybrid system where you hook up quantum processors to classical so you can have them working together? Lots of possibilities that we're thinking about right now. OK, are you ready? What is quantum information science? With it, we leverage quantum scales of nature using individual atoms and subatomic structure. Okay? Cool. So let's think of it this way. The world is fluid. Think about, the storms that come through in East Tennessee, and everything is, you can be anywhere at any time, and you have choices to walk across this podium or walk up a ramp. But if you look down at the scale of one atom, or down to subatomic structure like electrons and photons, you can't live anywhere you want. Atoms can only live in a certain state, or like a step on a ladder. You have limited choices. But on the other hand, that gives you some powers you didn't know you had. Atoms can be in certain ones or zero states. That sounds like a regular bit. It turns out that they have spin up and down just like a bit, 1 and 0. Okay, so that's the key of quantum computing is you have this 1 and 0 option. But subatomic little objects can actually be between 1 and 0. They can be like a combination of the two, and you don't have to figure out whether it's 1 or 0 until you look at it. And that provides us a benefit because, okay, imagine you're a mouse. You put a mouse in one of those mouse cheese mazes. You send the mouse off, and he goes to find the cheese. Mice are smart. So you take another mouse, or the same mouse, you stick him in there, and he finds another path to get the cheese. And you put him in there over and over, he finds all these different paths to get the fastest path to a cheese. That's what a computer does. It uses algorithms to find the fastest ways to do things. If you have a parallel computer like Frontier, you put lots of mice in there, and they all go at the same time and find the fastest path. That's parallel computing, eating a lot of cheese. But mice are expensive, right? And we don't like to have a lot of mice around. With a quantum computer, think of it this way. You only have one mouse, but he can go to all those places at the same time and find the answer for you with just one mouse. And you don't even need to know where he is till you ask him. And he says, here I am with the cheese. So you don't need all the energy, but you can get all the speed. That's the promise. I'm glossing over a lot of caveats. Lots. And if you buy me a drink at the free bar later, I'll tell you what they are. And then there's another benefit, which is you can take these subatomic objects, and they have this spin I talked about. You can separate them far from each other, and they retain that knowledge. So when they're really far apart from each other, they keep that information. So you can transmit information very far away, very quickly, and very securely. Because if you muck with one of them, the other knows it. That's much more secure than the internet that we have now in transmitting data. So if you can do things more efficiently and more securely, that's the innovation revolution that we could realize. Again, couple of provisos, couple of caveats, but this is where we're going, and we're already showing this at small scales in the laboratories and working with a lot of our partners to figure out how to really do something interesting with it. At Oak Ridge, we're focusing on several key areas. We have a long history of doing materials. Quantum materials means you're leveraging that special behavior I told you about atoms to make really exotic and neat materials that do exactly the kind of things we want, that eventually could scale up to the large scales. We're looking at sensing and networking. That's when I mentioned transmitting that data far away. And computing, which is where I sit. Quantum computing could really provide that energy efficiency we gain so that you can stick it in your pocket. Don't ask me how to stick a quantum computer in your pocket yet. But we're doing things like we have a quantum science center where we're investigating all these different types of materials to really build computers. We're looking at the applications you can do once you have a quantum computer. And we're looking at, we have the Quantum Computing User Program. This program is basically cloud access to a bunch of different vendors. So we're playing with all those different types of quantum computers to see which one works well for which application, which one can scale up. Because we don't know yet. But we're going to figure it out, and then we can tell and communicate with industry and other people who want to build these things, as part of a company. We're doing that hard work because we think it's cool, and then we're going to translate that out into the world. And we think that there's a lot of potential there. So what can we do? With quantum computing, what's the big application we want to go after? And we think there could be many, but this is one that's especially interesting. With Frontier, that largest supercomputer in the world I just mentioned to you, we were able to take all of this data from the Western grid. This is everything about solar power, wind power, nuclear. Take all that information and collect it up together, and within 15 minutes on the Frontier system, do a power analysis, a flow analysis within 15 minutes. In other words, we created a scenario where something went wrong, wind power shutdown, and then deployed all that data together and then figured out how the grid should react. That's super important if you think about it. If there's a wildfire or something else going on, you need to know how to optimize your grid and deliver that energy to everybody. With quantum computing, we're hoping we can do that in real time. That's the promise if we can make this work. And we'll need all those tools I just mentioned, the materials design, sensing, being very, when you're down to the subatomic structure, being able to see things more minutely. And of course, these networks transmitting the information and then bringing it all together. Probably using a classical computer to do all that optimization, but then deploying it back out, maybe on quantum computers. So having that quantum classical hybrid system yet again. And when we do that, and this is our roadmap, this is where Oak Ridge is thinking we want to go, and working with all of DOE and our partners at these other laboratories, because we can't do it alone. Industry and universities, we think that we need to deploy a secure and synchronized quantum network of computers and sensors. Because you're going to need all that. In order to bring all that information together and deploy it, that's what we're going to need to answer all these science questions. We're going to need applications and national security and sensing to figure out how to make it all happen securely. We'll need to look at pathways for quantum information, all those mice looking for the cheese. We're going to need all that. So here's the regional vision. First of all, we've been working with EPB for over a decade. You heard earlier, Tim Kelly mentioned that we've been working with them to do a lot of science and technology on the grid, on vehicles technology. And back in 2020, in fact, I remember it was March of 2020, a very auspicious month, we all went down to EPB to demonstrate a quantum network. We actually demonstrated and transmitted that data across multiple substations, working with EPB and Cubatech and Los Alamos, all together to demonstrate this quantum network. And then we all went home for a little while. And then they came up with a commercial quantum network, the first in the nation. And that's the kind of technology collaboration we want to do and build that. And as of just this year, we sat down and formed a collaborative with them so we can figure out how to build their network and ours and work together. So how do we start? Well, first of all, they have their commercial network, and we have a network. We actually have a pretty long quantum network. I mean, it's hard to know who's the longest. Right now, it's not in the US. But we have the longest that we know of quantum network that we do research on. And a local network's very useful, because that's where you play. That's where we're developing all the technology of repeaters and routers and all the things you need on a classical network we're going to need to figure out with quantum, too. Because quantum is touchy, as I mentioned. There's this error, and it has to be a little chilly. All these things you need to figure out quantum networks, we're playing with and doing research, both at EPB and Oak Ridge. And we're working with UTC, we mentioned Chattanooga, we're working with UTK, and we're working with our other university partners, and bringing in industry when the time is right. So while we perform that research, we also can think about how to connect the networks together. So we're working at the regional areas, I should say even the local areas, towns and cities. Then we connect it by satellite. You actually shoot a photon up and shoot it down using that quantum connection I mentioned, and be able to transmit information. Next, we connect them over fiber. TVA has fiber. They're transmitting stuff all day long all over the area. We can access that fiber. We're talking to them now so that we can have some of that fiber to do both classical and quantum networking. This is a collaboration that's starting to happen. And the neat thing is the Southeast is a great place to do this. Our cities are nicely distant apart, unlike some places where they're all together. We're actually a little spread out, which allows us to build all this technology together. And we have a lot of very interested people who want to join us. We can't do it alone. As I mentioned, you've got to have local networks and then the regional, and then we're going to hook up nationally. We're going to hook up to Chicago and the work with the quantum networking they're doing there. We're going to hook up to ESNet, which is out in California. We're going to hook it all together and make a national quantum hybrid network. That's the dream. And so with that, I'd like to say we're going to have a conference in Knoxville. I hope India likes the economic boost we're going to give her. And have this in late October. It's a technical conference, so there's going to be a lot of not just mice with cheese, but real, entanglement and spin conversations going on. But we hope you'll be interested and follow what we're doing and start to work with us so we can build this. This is something we're very interested in bringing to fruition, and we hope that that's something that will interest you too. So as far as building that $100 million quantum computer, we're happy to play with the computers right now and let you know how it goes. Join us, and then we'll figure out what that looks like long term. Thank you very much.